everybody, this is Mrs. Ewald signing in, and today we're going to go through gas laws, and we're basically going to be going through these four. First one is Boyle's law, then Charles' law, Gay-Lussac's law, and then combined gas law. You can also find these in your book in sections 13.2 to 13.4. So let's go ahead and just jump right in. Let's get gassed up here. So properties of gases. We looked at these when we did the It's a Gas activity, and these are the four different variables when we look at gases. And so you could predict the behavior of the gases based on the following. So the pressure, the volume, the number of particles or moles we could use now, and then also temperature. And so to represent pressure, we use P. Volume will be V. The number of particles or moles, we use a little n to represent that, and temperature, T. Please remember that temperature is going to be in Kelvin, and we'll talk more about the actual applications of that unit when we get to each of the different laws. So let's go ahead and start with Boyle's law. It is very important to make sure that you understand the law as well as be able to associate it with the name. So Boyle's law is dealing with, and let me move this, sorry, so you could see pressure and volume. So down here is volume, it just gets cut off. So we look at the relationship between pressure and volume, and they are inversely related. As far as our constants, we're going to have a constant number of particles or a constant number of moles, and temperature will remain the same. So when you look at this, then pressure would be inversely, or actually the pressure is proportional to the inverse of the, so it's 1 over volume. And just as Ms. Heaton was able to do when we did our trends podcast, she went through inverse relationship versus a direct relationship. And so this shows you then that pressure times volume will give you your constant K. And so, taking into the account of the relationship between pressure and volume, it's an inverse relationship. So pressure and volume are going to appear on the same side of the equality. We can then compare before and after we look at a specific gas. So the P1, V1 initially, and then the final P2, V2 after. And so as one goes up, the other goes down with pressure and volume. Pressure and volume. So this shows you a simulation of that relationship. So as the pressure goes down, the volume will go up. Notice the number of particles remain the same, and the temperature remains the same. This here gives you an example of how pressure and volume are inversely related. And also, what this is a gallon, well, a huge tank. And because it was not pressurized or didn't have enough gas inside, what happened is the pressure outside was greater than the pressure inside, causing it to collapse. So Charles' law. Now we're looking at volume and temperature, which is on the x-axis. Volume and temperature are directly related. So assuming constant number and pressure, as the volume goes up, the temperature will go up. So as one goes up, so will the other. That's why we see this direct relationship. So the volume is proportional to temperature. So now volume over temperature will give you your constant K. And we see it like this equality. So V1 over T1 is equal to V2 over T2. So there's the 1 and there's the 2. So this is Charles' law. Please make sure you can associate it with the name. This shows the simulation then of Charles' law at work. So as the temperature increases, the volume increases. Notice the pressure is remaining the same, and the number of particles inside is also remaining the same. This here shows you Charles' law, and we're looking at the temperature versus the volume of the balloon. So at a high temperature, the volume inside the balloon remains large. So the volume of a balloon at room temperature, this would be initially, or your V1 and T1 at this specific temperature. And then at the second temperature, much lower at 5 degrees Celsius, the volume of the balloon decreases. Gay-Lussac's. Now we're looking at pressure and temperature. This is also when we're assuming the same number and volume is going to be constant. So as the temperature increases, the pressure will increase. So it's a direct relationship. Pressure is proportional to temperature, and this is the equality. P1 over T1 is equal to P2 over T2. So again, as one goes up, so will the other. This here shows you then, as the temperature increases, the pressure will increase. And so that shows you that law at work. So if you think of a tire, so let's say we go on a trip. So this is the car before the trip. You check the pressure gauge, right? You make sure everything's good, everybody's happy. You got your treats and everything. And the car says, okay, let's get on the road, dude. So the car before the trip, and then the car, think of a tire, think about what's going to be happening. What do you think is going to happen to the pressure inside the tire? Well, the car after a very long trip is going to be pooped, right? And the pressure gauge is going to be much higher. And that relates to the temperature because of the friction of the tire with the road. So this here shows you a summary of the 3 laws that I just went over. It gives you the name of the law. You need to understand that name, be able to associate it with the relationship. So Boyle is pressure and volume. It's an inverse relationship. This is the equality we use, and the constants are temperature and number of moles. Charles is a direct relationship between volume and temperature. This is the equality. It's now volume over temperature is equal to volume over temperature. Pressure and number of moles remain constant. Gay-Lussac's, pressure and temperature are also a direct relationship. This is the equality. Again, it's going to be divided on both sides. And then volume and number of moles remain constant. So let's go through an example. The first thing to do is to always look at what are your givens and write those out. So here's a gas law problem. We have a gas pressure of 765 torr, so this is our pressure, at 23 degrees Celsius. We need to make sure that we now convert degrees Celsius into Kelvin. And how to do that? Well, you just take 23 degrees Celsius plus 273 to get 296 Kelvin. So you must use Kelvin while you're doing the calculation. And the pressure later is 560 torr. We want to know what the new temperature will be at that pressure. So that is what we're solving for. So you should be able to think about, okay, this is Gay-Lussac's law. And then think about the equality for that. And so this is P1 over T1 is equal to P2 over T2. So we have our given. The next thing to do would be to fill it in. And so it would look like this. We would have our first pressure, 765, over our first temperature, which is 296, equal to the pressure of 560, and what is our T2? Now we're going to cross multiply. So in your calculator, you would take 296 times 560 divided by 765 to get our answer. And now the question is, well, how many significant figures? We have 3 sig figs here, 3 here, and only 2 here. But we needed to convert this to Kelvin. And we're going to end up then with 3 sig figs, which is what you see here. So we're going to end up with 3 sig figs in our answer, which will be 217 Kelvin. Gas law problem number 2. Now we're looking at a volume and a temperature. So identify your givens. This has to be Charles' law. We were dealing with volume and temperature. V1 over T1 is equal to V2 over T2. We have the volume initially and the temperature initially, converting that to Kelvin, and that's our volume. We're solving for this, and this is our new temperature. So now we just plug and chug, put it into the equation. 473 over 309 equal to V2 over 367. Again, cross multiply, take 473 times 367 over 309. I'm showing this only because a lot of people make silly errors when they go to calculate. So I wanted to show this. Make sure you're practicing with me. We are going to have then 3 significant figures. Remember, we converted these two to Kelvin with 3. And so this will be 565 cubic centimeters. And that is our new volume. Always make sure that they make sense too, because we know that this relationship is a direct relationship. So if we are increasing the temperature, our volume should also be increasing. Make sure it makes sense. All right, here's one more. Now we're looking at Boyle's law. And Boyle's law is an inverse relationship. So we have P1 V1 is equal to P2 V2. So our initial pressure is 150. Our initial volume is 100 mil. Our P2 is 200. And our V2 is what we're solving for. And so you just go ahead and simplify this, divided by 200 to get our V2. How many significant figures? We have 3, 3, and 3. We need to have 3 in our answer, 75.0 mil. Plug it into your calculator. Make sure you know how to do the calculations. Understand how I'm getting my units at the end as well. They should all be canceling out and be left with mil. Combined gas law. Good news. You don't need to remember all 3. All you really need to do is know the combined gas law. Hence the name combined. What do you think it means? It means all the laws put together. And so the only thing that remains constant is the number of gas particles, or your amount of mole. And so this is what it looks like. P1V1 over T1 is equal to P2V2 over T2. It's really fun to say. It's not related to R2D2, although that'd be really, really cool. But again, it's just fun to say. And so if you look at this part of the combined, you notice you should be able to see Boyle's law. Looking at this, we see Charles' law. Looking at this, we see Gay-Lussac's law. So it's a combination of all 3. And so here's an example then of the combined gas law as it comes out here. And it's telling you that it's at STP. Remember, if it's at STP, we want to know what it would be at STP. So at STP, it would be at 1 atmosphere and 273 Kelvin. Because standard temperature and pressure, those are the requirements for that. So we're going to use P1 V1 over T1 equal to P2 V2 over T2. Notice I already have my variables, my givens identified. So these are all of the initial, and at the end we want to know what they will be at STP, which is written down here. So this is 1 atmosphere. So we're going to plug it into the equation. So 0.750. The volume is 30. Notice I'm just dropping my units for all of these to keep it simple. You should notice how they all cancel out. So you could show that in your work. Okay. Now when you go ahead and put this in your calculator, you're going to cross multiply again. So it'll be 0.750 times 273 times 30, all divided by, use parentheses, 313 times 1. Close parentheses. Get it from your calculator. How many sig figs should we have? We have 3, 3, 3. We're going to use 3 here, so we end up with 3 in our answer. We're solving for V2, so this will be 19.6 mils. Done. I would like for you to do one more on your own, but make sure you're careful of the units on either side of the equality. They need to match in order for the units to cancel. So this would be a way for you making sure that you practice your units and understand how they cancel and how they work. So notice you have a volume, and then you also have another volume. Note the units. You have your temperatures. You're solving for the other temperature. Here's a hint. You need to use Kelvin in the equation. So if it's given to you in degrees Celsius, convert it. And if they want the answer in degrees Celsius, you convert it again at the end. Okie dokie. So go ahead and try that out. Good luck. Have fun. Here you go. Just a summary of all of it. For each of the gas laws, can you identify the equation, identify the relationship, identify the graph shape, and also correctly choose which equation to use to solve a problem. Make sure you know which one is which scientist or which scientist does which law. All right? So, that's the end. Mrs. Ewald signing out. Happy gas law calculating. Peace out.